Okay. You're all done? Okay. This. Boys and girls, does everyone have the little note package that I gave them? Notice that this one's not incredibly long. It's just 3 little lessons. Okay. Everyone have one of these? Okay. If I missed you, please let me know. Pretty sure everyone has one, considering I only had one left over. Okay, this might look familiar here. What you see right here. Have we seen this before? Does it feel like we've seen this before? Yeah, we actually we have seen this almost exact same thing, except a lot of the time. Actually, no, I think this is actually it. This is copied and pasted from the previous lesson, and in chapter 3 actually is what it was. We were only we're only really concerned with quadratics that were in this form, and we kind of graphed them and we looked at them, and that was when we pointed to the vertex, we pointed out the step pattern, we pointed out the y-intercept, the maximum value or the minimum value, whether it was opening upward or downward, right? All that awesome information. And the same is true. We really want to reiterate that when the a value here out front of y equals x squared, that a could be y equals 2x squared, y equals 9x squared, y equals 1/2 x squared. That number is positive. This thing is going to open up. Yeah? The vertex will be 0, 0 whenever it's in that form, which means that the equation of the axis of symmetry, which we know as the x value of the vertex, is going to be 0, of course. And then there was this step pattern, which was a little bit weird. And we're going to really explore the step pattern today in detail. But what we did know about it was that we started at the vertex, and every time we go over 1, there's some sort of pattern that occurs, and it's almost like you're counting by the odd numbers. So for example, over 1, up 1. Over 1, up 3. Over 1, up 5. And that was the pattern. It was like 1, 3, 5. Yeah? And because parabolas are symmetrical, that same pattern existed on the other side, right? Left 1, up 3, up 5, and that's always what happens. Now, a lot of the times I'm only going to work on one side of the quadratic or one side of the parabola because it only makes sense to, because these things are symmetrical, and what you see on one side is literally the spitting image on the other side. Now, when that a value here and out front of y equals x squared is negative, so like negative 0.5, like negative 1/2, negative 10, negative 3, doesn't matter. If it's negative, this whole quadratic opens down, and we know that. We got really good at that. Now, if it's in the form y equals ax squared, then yes, the vertex is going to be 0, 0. It's going to create a maximum point. Okay, sure. Axis of symmetry still 0, and that step pattern changed from going over 1, like it's still 1, 3, 5, except now that the a value is negative, it's negative 1, negative 3, negative 5. Yeah? I mean, some of us on our in-class assignment had missed the negatives. And I wrote in there, hey, be careful. And I still gave it to you because I know you know what's going on. And that was too early to really attack that step pattern. But I really wanted to plant a seed in that unit because this is the unit where we really use that step pattern. And it's really useful. As far as we know, folks, before we even graph this thing, can we first graph, maybe in a different color, the graph of y equals x squared, which is the basic quadratic. We know y equals x squared has a vertex at 0, 0, and then it has coordinate 1, 1, 2, 4, 3, 9. It's like that. Because I'm thinking in my head, y equals x squared, I'm thinking to myself this. I'm going to do a table of values here. Here's x, here's y. I'm going to go negative 3, negative 0, 1, 2, 3. And all we're doing is we're squaring these. Yeah, because y equals x squared. So we're replacing this x here with the x values that we have. And this shouldn't be any concern or surprise because last year you worked with tons of tables of values. This year we really graphed this thing a whole lot already. So it should be 9, 4, 1, 0, 1, 4, 9. And that's where these coordinates that I'm plotting here are coming from. So -1, 1, -2, +4, -3, +9. We can even go ahead and say 4 is 16, yeah? And that would mean, on the other side, 4 goes up to 16. And I'm going to try my best here to draw a smooth curve, which we know is a quadratic function. It's y equals x squared. It's a parabola. And that's the basic, in grade 11, they'll call this the parent function, yeah? The parent quadratic, because it's the one that we always refer to. Whenever we're talking about quadratics, we're like, oh, what happened to this one? Well, let's compare it to y equals x squared. It looks like it did a little bit of this, a little bit of that, and we always go back to the parent, which is y equals x squared. But in this particular question, it's talking about y equals 2x squared. Yeah? That's the quadratic we're really talking about here. So they want us to make a table of values for y equals 2x squared. And this is where using your calculator can really come in handy. It's, again, you can type that in like that and then go into the brackets. And you know what? You're going to put in a -3 in the brackets here. You're going to put in a -2 in the brackets there. And you have to show all your steps, like all of your math here. Not exactly, because we're going to learn a beautiful way to do this without a table of values. So think about it. 3 squared is 9 times 2, 18. Yeah? 2 squared is 4 times 2 is 8. Let me know when I mess this up, because mental math in the morning, this one should be 2. Now, 0 squared is 0 times 2 is still 0. And because we know these things are symmetrical, watch what happens. These things are symmetrical. 2 times 1, 1 squared is 1 times 2 is 2. 2 squared is 4 times 2 is 8. 3 squared is 9 times 2 is 18. And these are our x, y coordinates. And I'm going to graph this one in a new color. So if you're taking a note here, maybe a new color. I'm going to use blue for the y equals 2x squared. So I'm going to start with -3, +18. Here it is. I'm going to go -2, +8, wherever that might be. Oh, it's hard to read. Is that +8 yet? -1, +2, 0, 0. And it's so lovely. Once you do 1/2 of this thing, you can just kind of, I mean, you can use this over here, 1, 2, but you can just look, this is the vertex clearly, right? So we know that we're going to go up here and 1 away, and 1 away. You know what I mean? 2, 8, 2, 8. Or you can say it's 2 away from the vertex. Yeah? And then lastly, 3, 18, way over here. And again, trying my best to draw in this smooth curve of a different color. There it is. So we made the table of values from -3 to +3, okay. Starting at the vertex, calculate the step pattern. Okay, well, let's calculate the step pattern. Maybe over here we'll say step pattern for y equals x squared, and then we can do the step pattern for y equals 2x squared, like that. So looking at the red one, over 1 up 1, over 1 up 3, over 1 up 5, over 1 up 7. And we're not surprised. 1, 3, 5, 7. That's usually what it is. So we can say SP is 1, 3, 5, ... 3 is enough. Now, let's have a look at the blue. It's over 1 up 2. You see that? Over 1, 1, 2, 3, 4, 5, 6. Up 6. And then over 1, up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the step pattern for the blue one here is 2, 6, 10, dot, dot, dot. Step pattern equals. It says here, what do you notice from the original step pattern of 1, 3, 5 to the new step pattern of 2, 6, 10? What happened? Each value in the original step pattern is multiplied by 2. Why do you think that is? What influence did that multiplying 2? Yeah, this right here. It's 2x squared. It's that a value. So what happened is this original red graph got squished a little bit. It's more narrow. Yeah? It's much more narrow. You can see it. And that's what that 2 does. When it's a 2 there, yeah, it makes these things a little bit more narrow. What do you notice from the original step pattern? You say the original step pattern. Original step pattern is multiplied by 2. Interesting. Questions? Okay, let's see what happens in this next one. First, is this counting by 5s or am I blind? It's counting by 5s, yes? Can you see it better on yours? I got to step back. Or is it counting by 3s? Yes. On your paper, it shows up a lot better, no? No, not much better. So we're going to use the graph y equals negative 3x squared. And we're going to first make a table of values. And this right here, if you're wondering what this mumbo jumbo kind of means here, it's saying make a table of values to graph the function when, if you look on this side of it, it says when x is greater than or equal to negative 3. And then if you look on the other side, it says when x is less than or equal to positive 3. Really what it means is, okay, between negative 3 and positive 3, make your tables of values. So, we're going to first sub in negative 3 into here. Yeah? Negative 3 squared is positive 9 times negative 3, negative 27. Yeah? Negative 27. Okay. Negative 2 squared is positive 4 times negative 3 is negative 12. Is that what that is? Okay, negative 1 squared is positive 1 times negative 3 is negative 3. 0, 0, yes. And because these things are symmetrical, we could almost just not even think for the rest of them. It says, oh, we got to graph this thing. So, I'm going to do, is negative 27 down here? Negative 3, negative 27, okay. Negative 2, 3, 6, 9, is this 12 here? Wow, this graph. Negative 1, negative 3, 0, 0. And because this is symmetrical, life gets nice. We graph all these points. We draw in our smooth curve as smooth as possible. Okay. Not the worst. It wants us to calculate this step pattern next. Actually, you need more time to graph that thing because it's really difficult, I know, to see the... I thought I had fixed these. I didn't fix these. Okay, let's step pattern. Now, this is where step pattern can become a little bit tricky because when I go over 1, down 1, see how my brain worked there? I even said it out loud. I said down 1. Time out. Down 1 really means down how many? I know it's down 1 box, but 1 box is worth 3. Yeah, so just be careful of that because that could come up. So this is really down 3. And then we go over 1 and down 3, 6, 9. Down 9. Over 1, down 3, 6, 9, 12, 15. Down 15. Notice when I say down, I put negative. It's almost like, remember slope? You go down 1 over 1, down 1, or something like that. Same idea here with step pattern. So what do you notice? What was the original step pattern of y equals x squared? Does anyone remember? Because this one's got to be drilled into your brain. If you got to absolutely memorize this, that's fine. But we need to know the original step pattern, which is who? 1, comma, 3, comma, 5, comma, and next would be 7, 9, and it continues. It does. Our step pattern of y equals negative 3x squared, step pattern, is negative 3, negative 9, negative 15, dot, dot, dot. It does go on. What happened? How are these similar or different? Or did you notice anything, Will? It multiplied each of the original step pattern members here by negative 3. Yeah? And we can't be too surprised because look, we actually have a negative 3 as our A value. Yeah? So, folks, I just want to see where we're headed. Yeah. This is what's going on here. Because we're relating everything we do to the parent quadratic, y equals x squared, a lot of the stuff that we kind of deal with relates back to this, and we can always compare it to this thing, and I'll show you what I mean. To calculate a step pattern, we're looking at our, so when I talk about our parabola, where I'm talking about this y equals negative 3x squared, we got to look at our A value. So our A value is, in this case, negative 3. Yeah? That's our A value. Then we're going to take our original quadratic step pattern, which we know is 1, 3, 5, but I'm going to write it a little bit differently. I'm going to write it like this. Because it was both Lauren and Vu that said, hey, it's just, or I think it was Will, sorry. They said, hey, we're just taking that original step pattern and it's multiplied by negative 3. So we're just going to grab the A value from our quadratic, and we're going to do exactly what they said. We're just going to multiply the step pattern by whatever the A value is. In this case, it's negative 3. So it's like, okay, 1 times negative 3, 3 times negative 3, 5 times negative 3, and what do we get? We get negative 3, negative 9, negative 15, which is a whole lot easier than graphing this thing and then trying to figure out the step pattern. Agreed? This is it. We love this. And I'm going to show you why we love this. In fact, you don't even need a table of values anymore, because the thing is, these quadratics in y equals ax squared form always have a vertex at 0, 0. Always. So have a look at this. It's like, okay, we'll graph this using the vertex, which we already know what the vertex is, and the step pattern. This will become the best and newest graphing method, and this table of values business will kind of become a little bit obsolete. It was almost like this. Remember when you were learning about lines in grade 9? You start at the y-intercept and rise, run, rise, run, rise, run. And that's how you graph lines, as opposed to making a table of values from -5 to +5, right? Like the table of values became quickly extinct. Very similar here. Now, hey, not discrediting the table of values at all. It's the best, most powerful way to graph, but there's also an efficient way to graph too. So we know that because these are in y equals ax squared form, their vertex is 0, 0. So we'll say, first, the vertex of this guy, I'm going to put v and then 0, 0. I put a v here just to remind myself, hey, that's the vertex. Okay. Now the step pattern, we know is 1 times something, 3 times something, 5 times something. What is our A value here? if this quadratic's in y equals ax squared, what's our a value here? It's 0.5. So maybe I'm going to write that. Okay, a is 0.5. I'm going to keep that information close. Now, I'm going to sub that in. 1 times 0.5, comma, 3 times 0.5, comma, 5 times 0.5. And this simplifies to 0.5, 1.5, 2.5. So, what we do is we start at the vertex 0, 0. Think about it. This quadratic has an a value is positive 0.5. So every time we go over 1, we're going to go up. We're not going to go down, right? So over 1, up 0.5. And I know that feels a little bit weird. Bear with me. From this point, over 1 and up 1.5. So there's a half and there's 1. Right there. From this point, over 1 and up 2.5. Just like that. And that's one arm of the parabola. And very quickly, and this is what I mean, it's so nice that parabolas are symmetrical because you can almost stop thinking about step pattern and just try to mirror the other side. Or, over 1, up 1/2, over another one, up 1.5, over another one, up 2.5. And then we try our best here to create some sort of smooth curve. Like that. Notice, this quadratic is a little bit compressed, don't you think? It looks like someone is putting pressure on it this way. Like it's much more wide. Yeah? Would you agree with that? If we think about our parent function, y equals x squared, shares the same vertex, but it's 1, 1, 2, 4, 3, 9. Yeah? 1, 1, 2, 4, 3, 9. And this right here in purple would be our parent function, our original parent quadratic. And if we're going to compare the y equals 0.5 x squared to y equals x squared, notice how it's a little bit widened. You see that? Something might have happened here. Interesting. And last, we're going to graph this guy here. What's our vertex for y equals ax squared? Our vertex coordinate, folks? 0, 0. And then our step pattern often relies on the a value, and we know that a equals -2. That's good information to have. So we'll say 1a, 3a, 5a. 1 times -2, 3 times -2, 5 times -2. And this simplifies to -2, -6, and -10. So we're starting again at 0, 0. We're going to go over 1, down 2, 1, 2. Oh, from this point, that's the key. From this point, over 1, down 6. 1, 2, 3, 4, 5, 6. From this point, over 1, down 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's one whole arm done. Now the next arm. Over 1, down 2. Over 1, down 6. Over 1, down 10. And I know it's down because these are negatives. Yeah? And we try our best to draw in this smooth curve. That is pretty good. That's got to be my best one. And it's not even that good. Anyway. Questions about that? The big idea here is this. This A value, it controls the problem. First of all, the A value, if it's positive, we know that the quadratic opens up. Yes? If it's a positive, it opens up. If it's a negative, we know it opens down. Fair? Now, what we're about to run into in this unit is that if that A value, I know it could be positive or negative, and we know what the positive and negative does, but if it's a fraction, if that A value is a fraction, like a number between 0 and 1, and I know, don't quote me, if it's a negative between 0 and 1, we're good. If it's a positive between 0 and 1, we're good. But take the negative positive out of this. If that A value is like 0.5, 2/3, 1/2, yeah? What happens is it kind of makes the whole quadratic wider. It's like it's getting squished, yeah? So if we say if A is greater than, A is greater than, is that the way we want to write? No, I think it's this way. Greater than 1. Hold on, I'm confusing myself. A is greater than 0. Oh, that's a better way to put this, folks. How about this? If A is greater than 1, or if A, and A is less than, guys, what's going on with me? I'm fumbling the ball here. Greater than 0. It makes the quadratic wider. Now, if A is greater than 1, any number like 2, 3, 4, 5, 6, it makes the quadratic more narrow. Okay. So I should keep that. Questions about anything? Will? What? That wouldn't be the original step pattern. Y equals x squared is like the original quadratic function. It's like the parent quadratic. It's the one that we always refer to. And its step pattern is 1, 3, 5, ... Okay. So folks, on 256, what do we got here? 1 and 3. I love 1. It's matching the quadratic to its picture. I love that. Number 3, write the equations of two different quadratic relations that match each description. So if it's narrower than this, or if it's wider than that, you know what's happening there. 4, A, B, C, D. I want you to sketch those ones. There's only 4 to sketch. Not so bad. Number 5 is to describe the transformations that were applied here. So you're going to have to look at these graphs and look at their step pattern and kind of see what was happening. And then lastly, number 11 is a beautiful chart that this chart could very well be seen on some sort of assignment. Great. We'd love to see this chart here. And that's it. I feel like that's good homework. This is important homework to do. Yeah? Good? Questions about anything? Will? Yeah. So for example, well, good question. If we have y equals 4x squared, is that going to make it more narrow or more wide? More narrow. Yeah. Well, now what about this one? Y equals 1/3 x squared. More wide. Yeah. What about y equals negative 1/2 x squared? More wide. I agree. But the only thing else that's different about this one is that it's negative. And what do we know about quadratics that are negative? Yeah. Opening down. Absolutely. Or some people might say it's reflected on the x-axis. Yeah. But I think they might want an example there. I think I know which one.